Okay, so we would like to state and prove one of the most beautiful and most useful at that theorems of elementary real analysis, the Cantor Intersection Theorem. So we're going to work in a metric space, and in particular, we're going to work in what is known as a complete metric space. And it's not too hard to guess what that means. So a complete metric space is a metric space in which every Cauchy sequence converges. Okay, let's try to be as detailed as possible here. So imagine that you have a metric space x comma d, then the sequence xn, n in n of elements of x is called Cauchy if for every epsilon greater than 0, there exists n naught in n, so that if n comma m is greater than n naught, then the distance between xn and xm is less than epsilon. And completeness implies that if xn is Cauchy, then there exists x in x such that the limit as n tends to infinity of the distance between xn and x is 0, which is when we write the limit as n tends to infinity of xn is equal to x. Okay, that's pretty much what it is. These are all the definitions that we basically need in our case. Now, there's going to be a couple of more reminders, but why don't we give the statement of the Cantor Intersection Theorem and then give the definitions that are needed. So here's the Cantor Intersection Theorem. It says that suppose that X is a complete metric space, and Fn, n in n, is a sequence of closed subsets of X such that, so we need them to be closed, and they should also satisfy, they form a decreasing sequence, meaning F1 contains F2, and F2 contains F3, and F3 contains F4, and so on and so forth. Please understand that when I write this symbol here, that doesn't mean necessarily strict containment. So F1 could be equal to F2, and F2 could be equal to F3. And secondly, the diameter of f sub n, as a sequence, as a numerical sequence, tends to 0. We will explain in a second what the diameter is. Then there exists x in x, such that the intersection of all these sets is just the singleton x. When I say singleton, I mean a set with one element. So pretty much what we learn here is that this sequence of closed sets pretty much intersects down to one element. Okay, so it is a good idea here to actually say a few things. So closed set, what is a closed set? A closed set is a set that does not let its sequences converge outside of it. So a set is closed if whenever xn is in F and xn approaches x, then x is in F. Now, closed sets can be shown to be complements of open sets. Open sets are the sets for which each point has an open ball centered at that point contained in the set. And let's talk a little about the diameter. So the diameter of a subset of a metric space, so the diameter of, let's say, set Y, is simply the supremum of all the distances of elements of Y. So D of AB for A comma B in Y. Okay, I would like to say maximum, but it's not certain that there are 2 points that at which that distance is assumed. I think the easiest example to convince yourselves that something like that is not necessarily occurring within the set is take the open interval 0, 1. Okay, it's easy to understand here that the diameter of this set is 1, because you can find elements that approach 0 on the one hand, 1 on the other hand, or pairs of elements rather, whose distances are very, very close to 1. But you will never actually get the distance 1 within inside that set. You will never get it. So this is what the prerequisites are. And let's prove this theorem. It has a very, very pleasant proof, very, very nice proof. So proof. So let's start by showing that the intersection cannot have more than one element, and that's a triviality. So the first remark is that the intersection does not have more than one element. Indeed, if x comma y both belong to the intersection, then x and y belong to Fn for every n. And that would mean that the distance between x and y, which is known to be greater than or equal to 0, at the same time cannot exceed the diameter of Fn. And now I think you can see what the problem is, that this tends to 0. So the number d of xy gets squeezed between a constant sequence and the sequence that tends to 0, and that implies that d of xy is equal to 0, which of course means that x is equal to y. So any 2 elements in the intersection have to be equal. Of course, nobody says that there exists something in the intersection, so that's yet to be proven. So if we show that the intersection contains at least one point, then will be done. And how is this done? This is done in the simplest possible way. So choose xn belonging to Fn. And here, of course, I obviously forgot to mention something in the beginning, that all of these sets should be non-empty. Okay, that's a very serious. So let me put it here, because one can understand that we could take just the empty set for all the Fn's, and pretty much we're not going to get anything in that intersection. So let's not take this omission lightly. I apologize for it. It's a very serious omission that would render the whole theorem false. So choose xn in Fn, which can be done now since we said that all these sets are non-empty. Then the sequence xn n in n is Cauchy. Okay, how do I know that? Well, the distance between xn and xm is greater than or equal to 0, of course, and it's less than or equal to the diameter of, let's say, Fn, assuming that m is less than or equal to n. Okay, so obviously these diameters tend to 0, so the sequence of these distances should tend to 0, but it might be a better idea to actually give the argument more rigorously. So let epsilon be greater than 0. Choose a knot such that the diameter of f of a knot is less than epsilon. Then, if n comma m are greater than a knot, xn comma xn belongs to Fn, which is a subset of f of n naught, right? And yn belongs to Fm. There's no y here. Sorry about this. Xm belongs to Fm, which is also a subset of f of n, f sub n naught. Hence, the distance between xn and xm is less than or equal to the diameter of f of n naught, f sub n naught, which is less than epsilon. And that shows in a very rigorous and maybe unnecessarily formal way that this is a Cauchy sequence. So let x, since we said that we are in a complete metric space, so let x be the limit of xn. By the way, it's a very simple argument to show that if a sequence in a metric space converges, then the limit is unique. So let xn be the limit of xn. We need to show that x belongs to Fk for any k in n. Yes, but x is the limit of the following subsequence. So what we do is we take x sub n for n greater than or equal to k. Okay, so we choose this subsequence of xn by taking all the indices that are greater than or equal to k. This sequence belongs, this sequence is in Fk, and x has to belong to Fk. Since it is its limit. So this is true for all k's, i.e. x belongs to the intersection of all the fn's, and this is the proof of our theorem. Now, it's kind of funny here to understand how important all of the conditions are. So, for example, I said that the sets have to be non-empty. If you can make them all empty, and then you will get an empty intersection. Or X has to be a complete metric space. For example, if you take an incomplete metric space, a very simple incomplete metric space is take the real line and take away the point 0. Then it turns out that if you take all the intervals 0, 1 over n, all of these intervals in this space, they're actually closed. Okay, believe it or not, they're closed. If you think about it, no sequence, the fact that we're removing 0 is will not make this set, or rather, since 0 does not belong to our set, the subset 0, 1 over n will be closed, because if you take a sequence that converges somewhere, that thing cannot be 0, and if it's anything else, it has to be inside this interval. Of course, this space is not a complete metric space with the usual absolute value, and if you take the intersection of all the sets, you will see that it's empty, meaning if the metric space is not complete, the theorem obviously fails. Then if the diameter of the sets does not tend to 0, the theorem can fail in more than one way. So for example, if you take the same set over and over and over, its intersection is itself, so the intersection is not obviously a unique element, but you can have crazier things. So if you take Fn, if again you don't assume that the intersection is, I'm sorry, that the diameter goes to 0, you could take Fn to be n, n plus 1, n plus 2, and so on and so forth. This is a closed subset of R. Everything else is satisfied. R is a complete metric space. This is a sequence of closed sets. Each set is contained in the previous one. It's a decreasing sequence of closed sets, but certainly their intersection is empty, okay, because their diameter doesn't tend to 0. Let's see, is there... Okay, and then obviously, I mean, if you don't take the sets to be closed, if you take the sets to be open, it's very easy to, even in a complete metric space, to make to have them have an empty intersection. Again, you could take the sets 0, 1 over n, their intersection is empty, and this fails because they're not closed. And of course, I shouldn't be implying in any shape or form that since the sets are not closed, then they have to be open, but I just took these sets as examples of non-closed sets. So in this sense, it's a very sharp theorem. And one of the reasons of giving this theorem in detail is because it's used in an essential way in the proof of the Baire category theorem. And that's all. Thanks for watching.